Clean agent fire suppression in mission-critical environments operates on a strict mandate: interrupt an active electrical spark without leaving residue or causing collateral equipment damage. Achieving this requires injecting a precise mass of inert gas into a specific volumetric space. If the physical enclosure deviates from the mathematical model used to calculate that mass, the gas concentration drops below the suppression threshold, and the fire continues to burn. This application map delineates valid engineering geometries. Inert gas is highly effective for ICT network rooms and coordinated electrical switchgear up to 480 volts. It is ineffective for unsealed, highly leaky spaces or deep-seated reactive metal fires. Furthermore, standard inert gas strategies cannot contain lithium-ion thermal runaway propagation, which requires a separate, dedicated containment strategy. Protecting these valid geometries introduces the overarching rule of clean agent architecture: never combine listings. An engineered system relies on precise fluid dynamic testing. Mixing cylinders, flow-regulating valves, acoustic nozzles, or calculation software from different original equipment manufacturers invalidates the listing. The flow coefficients of one manufacturer's valve will not match the algorithms of another software, leading to unpredictable discharge timing and pressure spikes. This chart outlines the rigid hierarchy of regulatory authority governing these designs. Local AHJ requirements, such as DOMCAR conditions in Indonesia, form the legal baseline. Above that sit the adopted technical standards, like NFPA 2001 and ISO 14520. However, the exact OEM-listed software limits override generic code minimums. When determining system constraints, engineers apply the most stringent applicable requirement from this hierarchy to secure design approval. This diagram illustrates the required chain of custody for a compliant installation. The process moves sequentially from defining the precise enclosure to the hydraulic calculation, through the logic of the releasing panel, to the physical discharge performance, and finally to post-event recovery. Breaking any link in this chain compromises the concentration hold time and occupant safety. Mission-critical reliability relies on strict adherence to this standard-driven lifecycle. Generic engineering equations are insufficient. Extinguishment is only guaranteed when the exact physical dimensions of the hazard are locked in place and subjected to a fully traceable, witnessed test sequence. The engineering lifecycle begins with defining the hazard and mapping the exact boundary of the physical enclosure. For an energized Class C data hall, this requires capturing every cubic meter of connected space that the inert gas will occupy during a discharge event. Consider a standard data hall measuring 50 by 30 meters. To calculate the gross connected volume, we measure the 4.5 meter main room height, but we must also include the 0.9 meter raised floor and the 1.2 meter ceiling plenum, because these zones remain open to gas migration. Multiplying the footprint by this combined 6.6 meter total height yields a gross connected volume of 9,900 cubic meters. From this gross volume, we subtract impermeable solids. These are permanent, perfectly sealed objects that displace the gas. In this data hall, the structural concrete columns and sealed perimeter structural bulkheads amount to precisely 75 cubic meters of displaced air. Subtracting this from the gross volume refines the calculation. A common failure point in enclosure surveys is the mischaracterization of permeable equipment. You do not deduct items the agent can enter. Server racks, cable trays, and ventilated electrical switchgear contain air pockets and cooling pathways. Because the inert gas will permeate these spaces, their volume must remain in the calculation. Retaining them results in a finalized net design volume of 9,825 cubic meters. An inaccurate net volume survey guarantees incorrect agent concentration calculations. If the volume is overcalculated by ignoring solid displacements, the system will deliver too much gas, generating excessive room pressure. If the volume is undercalculated by improperly deducting permeable server racks, the resulting gas concentration will be too lean to suppress a Class C fire. The accuracy of the physical survey dictates the success of the physics. With the net volume frozen, we must determine the exact mass of agent required. This requires translating the geometry of the room into the physical properties of the gas, using the specific volume equation. The specific volume of a gas, its physical footprint per kilogram, expands and contracts based on absolute temperature. Therefore, the equation must be corrected against the most extreme operational states of the room. For this data haul, we calculate against a minimum expected temperature of 18 degrees Celsius and a maximum expected temperature of 32 degrees. We size the total required agent mass based on the minimum room temperature. At 18 degrees, the air is cold and the gas density is at its highest. Designing for this state ensures the system holds enough physical mass to achieve the target concentration even when the gas is maximally compressed by the cold environment. Applying this to a mixed gas IG-541 system, protecting an energized Class C hazard, FM global standards and OEM listings dictate a minimum design concentration of 38.5%. Factoring in the specific volume at 18 degrees Celsius, protecting this 9,825 cubic meter room requires exactly 6,813.7 kilograms of agent. To translate this mass into hardware, we divide the requirement by the capacity of the storage cylinders. Using standard 80-liter cylinders pressurized to 300 bar, each unit holds 33.3 kilograms of IG-541. Dividing 6,813.7 by 33.3 yields 204.6. Since we cannot install a fraction of a cylinder, we round upward, requiring a duty bank of exactly 205 operating cylinders. If we run the same room parameters using IG-100, which is pure nitrogen, the physics shift. IG-100 requires a higher 41.9% concentration for energized Class C hazards. Because pure nitrogen has a different specific volume and requires a higher concentration, achieving suppression in the identical room requires 254 operating cylinders, significantly expanding the required physical storage footprint. Sizing cylinders at the minimum temperature guarantees extinguishment. The required follow-up is calculating the resulting peak concentration at the maximum 32-degree room temperature. When the room is hot, the gas expands. We must verify that this expanded peak concentration does not breach the allowable oxygen deprivation limits for human exposure. This diagram outlines the distribution network required to move the agent from storage to the hazard. Pushing gas from 205 high-pressure cylinders through complex pipe networks to remote nozzles creates extreme hydraulic friction. NFPA standards mandate a strict delivery window. The listed hydraulic software report must mathematically prove that the system can achieve 95% of the design concentration within 120 seconds or less. This time gate limits the production of toxic byproducts and halts the fire before thermal damage cascades through the electronic equipment. Generic pressure estimates are invalid here. The hydraulic calculation is only accepted if the exact isometric layout, including a 72-meter straight path, every elevation change, and the specific resistance of every T-fitting generates zero unresolved errors in the OEM software.
Any field rerouting of the pipe during installation voids the approved model and requires a complete recalculation. Beyond fluid friction, the violent decompression of 300 bar gas generates severe acoustic energy. A standard discharge nozzle can emit 118 decibels of high-frequency noise. Modern hard disk drives suffer degraded read-write performance or permanent physical failure when exposed to sound pressure exceeding 110 decibels. Screening this decay using the free field distance formula dictates a minimum safe boundary of 2.51 meters. To mitigate this acoustic threat, engineers specify FM-approved acoustic nozzles fitted with sound-absorbing materials. Furthermore, utilizing pressure-regulating valves slows the mass flow rate across the 120-second discharge window, and physical nozzle placement is engineered to ensure a minimum 4-meter separation distance from any sensitive storage array. Delivering this much mass into a sealed room creates extreme structural pressurization. Injecting 205 cylinders of gas in 120 seconds rapidly compresses the existing air inside the enclosure. Without mitigation, this overpressure will blow out ceiling tiles, buckle partition walls, and destroy doors. Preventing structural collapse requires massive, precisely calculated dynamic pressure venting. The required vent area is dictated by the dynamic peak flow of the discharge. For our IG-541 model, the gas expands into the room at a peak flow rate of 47 cubic meters per second. Factoring in the allowed structural pressure limit and the flow coefficient of the louvers, The calculation demands a minimum of 4.1 square meters of effective free vent area to safely exhaust the displaced atmosphere. The delivery architecture is highly interdependent. Adjusting the pipe diameter to fix a hydraulic delivery delay alters the peak flow rate. A changed flow rate alters the nozzle acoustics and immediately demands a recalculation of the pressure vent area. Delivery timing, sound mitigation, and structural relief operate as a single unified fluid dynamics model. Controlling this physical discharge requires strict logic sequencing. The releasing fire alarm control panel acts as the autonomous, isolated safety command authority. It owns the detection circuits, the release timers, and the valve actuation, operating entirely independent of standard building networks. The sequence of operations is absolute. A single smoke detector input registers an alarm and initiates investigation. A secondary, independent detector input, or a deliberate manual pull station, is required to satisfy the confirmed release criteria. Once confirmed, the panel triggers occupant warnings and starts the pre-discharge time delay. Building management systems and security operations centers receive status updates, but they are strictly monitor-only platforms. Network failure or a stalled HMI screen on a remote supervisory computer must never defeat the local releasing autonomy. The fire panel retains absolute physical control over the abort logic and valve command. The pre-discharge delay must be reconciled against the required safe egress time, or RSET. A standard egress calculation models 8 seconds for alarm transmission and recognition, 5 seconds of pre-movement decision time for trained staff, and 37.5 seconds to travel 27 meters to a remote exit. This totals 50.5 seconds of required evacuation time. By setting a standard FM-approved 30-second pre-discharge delay against a 50.5-second egress requirement, occupants remain inside the hazard zone while the system actuates. This mathematical overlap means personnel will face 20.5 seconds of post-discharge human exposure to the extinguishing agent as they complete their evacuation. Because of this exposure, we must check the peak concentrations at the maximum 32-degree room temperature. The IG-541 system hits 39.98%, keeping the residual oxygen at a manageable 12.5%. However, the IG-100 system reaches 43.48%, dropping oxygen below 12.1%. This specific concentration triggers strict regulatory scrutiny and requires applying adopted time-limited human exposure protocols. The integrity of the hardware, the precision of the mass calculation, and the speed of the hydraulic delivery hold no value if the control matrix fails to evacuate personnel before gas concentrations peak. The fire strategy must synchronize the physical suppression capability with safe occupant evacuation before live agent testing is even considered. System resilience is proven through operational edge cases. Consider a scenario where aspirating smoke detectors identify incipient smoke inside a heavily occupied control room. The first alert triggers local warnings, allowing trained staff to investigate the source without immediately initiating a dump. If the fire escalates and triggers a secondary detector, the panel confirms the fire, isolates the HVAC dampers to prevent gas escape, sounds the evacuation strobes, and commands the release sequence. The logic prevents a premature discharge while securing the room for agent retention. Alternatively, consider a scenario where the detection circuit suffers a supervisory fault, such as an open wire. The panel must isolate this error. If an operator physically verifies a fire, local autonomy ensures that actuating the supervised manual release station instantly bypasses the non-critical circuit fault to directly command the valve and execute the discharge. Following installation, the physical enclosure itself becomes the primary point of failure. A mandated door fan test pressurizes the room to measure cumulative leakage through unsealed cable penetrations and door frames. In a faulty room, the graph tracks the heavy inert gas sinking and escaping over a 10-minute hold period, plotting a dangerous trajectory toward the 32.73% failure threshold. The acceptance rule for enclosure integrity is absolute. If the predictive model shows the concentration dropping below 85% of the required design level at the height of the tallest protected equipment before the 10-minute mark, the test fails. The contractor must physically hunt down the leaks, apply approved fire stopping, and repeat the test until the room holds the gas. If a live discharge occurs, recovery is heavily governed.
Re-entry is strictly an authorized process, never an automatic reset. Incident commanders must maintain physical access control, utilize calibrated atmospheric monitors to verify safe oxygen levels, and engage approved mechanical exhaust ventilation to clear the inert gas before allowing technicians to assess the damaged server. Restoring the room to service requires physical intervention. Actuated cylinders must be replaced and manifold connections torqued to specification. Any structural changes made to the room during the repair process mandate updating the management of change documentation and revalidating the enclosure integrity with a new door fan test. Inert gas suppression remains a continuous life cycle of governed physical boundaries, mathematical proof, and uncompromising operational discipline. Extinguishment is only successful when the enclosure survey, agent calculation, hydraulic timing, and recovery protocols are executed as a single, unbroken chain of engineering evidence.